So let's talk about alternating current and transformers. Alternating current is the foundation of our electrical system, and the main reason it's a foundation, well, there's two reasons. One is because when we generate electricity using generators and induction, we generate electricity in alternating current, current that alternates. The other reason we use it is because it's easy to change voltages with alternating current. It's really hard to do that with direct current, and I'll show you how that works and why, and it's pretty straightforward. If you remember that when we were talking about current electricity earlier, we talked about the idea that we tend to generate electricity really far from where people live, power plants and dams and stuff. People tend not to want to live those places, but we need to use the electricity in where we live, in the cities. And so when we transfer electricity, we like to do it at high voltages so that we can use low current, so that we don't lose a lot of energy in the form of heat by transferring it. Well, the way we change voltages is by using transformers and alternating current. So I just want to cover that today. Okay, so AC generators. AC stands for alternating current. DC stands for direct current, for those of you that are big fans of AC/DC, rock and roll. Direct current is what we talked about with batteries and circuits. Batteries provide direct current electricity. Generators provide alternating current electricity. And when we generate electricity, again, it can be thought of as an electric motor in reverse. A motor takes electrical energy, turns it to mechanical energy. A generator takes mechanical energy and turns it into electrical energy. Where do we usually, for the electricity that we generate, where do we usually get that mechanical energy? We burn coal, okay, to make a lot of our electricity is generated using steam. So we burn coal to make that steam. What else? To turn turbines. Water, we use water from behind dams to turn them. We can use the wind and wind power. So we get mechanical energy in a lot of different ways. So remember last time we did talk about generators, and basically what we got is that a changing flux generates EMF, which generates current, okay? You can change flux in different ways. We could change the magnetic field, we could change the size of the coils of wire, or we can change the orientation of the coils of the wire. And the third choice is kind of what we usually do. By rotating coils of wire in a magnetic field, we get a changing flux, which produces an EMF. You can visualize that when the coils are perpendicular to the magnetic field, then you're going to have a maximum amount of flux. When the coils are parallel to the field, you will have zero flux, and that variation of flux will be like a cosine curve, basically. And this is what is the basis for alternating current. We get alternating flux, gives us alternating EMF, which generates alternating current, or AC. Here's a picture of what we're talking about. Notice that in this left-hand picture, the coil of wire has the maximum amount of flux possible, the maximum number of field lines going through them when it's oriented in this way. When it's oriented like the picture in the right, since the magnetic field is going into the board, there's no field lines going through those loops, so there's no flux. So we go from a maximum to zero, and as this thing rotates, you're constantly fluctuating from maximum to zero, maximum to zero, maximum to zero. That is alternating flux, which will generate alternating EMF, which will create alternating current. Okay? So let's look at what this is going to look like in graphically speaking. If, just like that last diagram, if this is the field, okay, and my coil of wire is oriented this way, that's when I'm going to have maximum flux. And in the same situation, this is when I would have zero flux as this coil is rotating. So I can start to make a graph over time of different quantities. One quantity I could look at is flux. Okay? And if we start at time equals zero when the coil is oriented this way, then my flux is going to basically look like this. A cosine curve, right? Now remember that Faraday's law says that the EMF that gets generated is equal to the negative rate of change of flux over change in time, okay, or the negative rate of change of flux. So what that means is, notice that on my graph here, on my y-axis I have flux, and on my x-axis I have time. So what Faraday is telling us is that the EMF is equal to change in y over change in x, or slope. So if I was to also graph the EMF that is being generated, remember EMF is essentially voltage, it would look something like this. And we're getting a sine curve, right? For those of you that have studied sines and cosines and things like that, okay? This green line, the EMF, is just a graph of the slope of the flux. So here's where the slope is maximum, here's where the slope is 0, and then so on and so on and so on. Make sense? Finally, if I was to add a graph of current over time, the current graph would also fluctuate with the EMF, and we would have current that's alternating between positive and negative values, and that's what we call alternating current. Okay, that's why we get alternating current, because of the way we generate electricity. Makes sense? Now, we talked about with motors, we took direct current and turned it into alternating current by using those split ring commutators. That's one of the differences between a motor and a generator. In a generator, instead of having split rings, we have slip rings. These rings right here, notice, are not split. They're continuous. And so as the armature rotates, you have a continuous contact with the brushes. Those are the same. And so the current that gets generated is alternating current. There's a couple of reasons for that. Split ring commutators, if you remember with the motors we used last week, do you remember when they were turning, you could see those sparks happening the whole time? This doesn't spark because you're not making and breaking contacts all the time, and there's less wear and tear, and it generates alternating current, which has its benefits. All right. Since the current and the voltage are alternating all the time, we're going to have to look at some ways to deal with that mathematically. So one of the things we deal with is peak voltage, okay, and peak current. And it's given this symbol, EMF, or E sub 0 is known as the peak voltage or the peak EMF, and it occurs when the flux is 0, as you could see in that graph that we just did. The current will vary with the voltage, with the EMF. And just like before when we were doing Ohm's law, with direct current, Ohm's law told us that the current in a circuit is equal to the voltage divided by the resistance. Well, this is the alternating current version of that equation. The peak current will equal the peak EMF divided by the resistance in the circuit. Since I have current fluctuating and I have EMF fluctuating, I'm also going to have power fluctuating. The power used by a device will also fluctuate, and it will always be positive, whereas, Vince, what you were just saying, the EMF and the current, you can have positive and negative values, but the power will always be positive. And again, this is very similar to our equation with direct current, where P equals IV. Okay? And our peak power would be, peak. If we just use the peak values for those, that we would get the peak power as well. So we've talked about peak current and peak voltage and peak power, but in some ways it would be nice to know what the average current was, or what the average EMF was, all right? But remember from our graphs before that current and EMF were fluctuating between positive and negative. So what would the average of those be? If I totally average that out, what would I get? 0. You have just as much positive as you have negative, and the average would be 0. But we know that we're using power. So if I try to find the average power by using the average current and the average voltage, I would just get 0, but that doesn't make sense because power is being used. So we need to do something different. And that's where this idea of root mean squared comes into play. Because the averages of power, voltage, and current can be helpful things to know, but they would be 0 if we did them truly. So instead what we do is we do a mathematical trick to get the average, but a non-zero average. So visually, here's kind of what it would look like. Let's just talk about current for now. Let's say current is alternating. And the averages of all of these currents would be 0, right? I have just as many positive as negative. So that's not going to help me. So what can I do? Well, the first thing I do is I square them all. And that makes everything positive, like this, okay, by squaring it. Then I take the average. Now I have everything positive, so I take the average, which would be something up here. Well, that's not truly the average because I squared everything. So I'll take the square root of my average, and it gives me a new number that is now a numerical value that is roughly the average if everything were positive, okay? No, it's just going to be a good, it's called the root mean squared value, and it's a good way of giving you an average even though the average would truly be 0, okay? Hold on a second. Now, fortunately for us, you guys, we don't have to do all this stuff. It's already done for us, and it turns out if we were to do this, if I was to square all the values, average them, and take the square root, I would basically get the same result as taking, no, I don't want that, I want this, okay? It's taking the peak value and dividing it by the square root of 2. It's essentially the same thing. So mathematically, it's quite easy to do. If I want to find the root mean squared value of something, say current, I take the peak current and divide it by the square root of 2. If I want to find the root mean squared value of voltage, I take the peak voltage, divide it by the square root of 2. And you can think of that as being a mathematical way of finding the averages for those things. So now if I want to find the average power being used, I take the RMS value of the voltage, the RMS value of the current, and voila, I do it, okay? Our outlets that we plug things into in our homes here in America, they tell us they have a voltage of 120 volts. But remember, it's alternating. It's alternating voltage. And the average voltage is really 0, right? Because it's just flip-flopping. So what is that 120 volts? When we say it's 120 volts, what are they telling us? It's the RMS value. It's the RMS voltage. So really, the highest voltage is higher than that. And I think you have a homework problem for that, maybe, if you haven't done it yet. And I think it ends up being something like 170 volts is the actual maximum voltage. 120 is the RMS voltage. All right, back EMF is another concept I just want you to be aware of. It's a pretty cool idea, but you have to be thinking forward and backwards to kind of think about it. So we have motors. Remember the idea of a motor. We take a coil of wire, we put current through it. If it's in a magnetic field, it feels a force and starts to rotate. You with me? That's what an electric motor does. However, when an electric motor is running, there is a coil of wire that's turning in a magnetic field, which is what a generator is. So there will be current that is induced in those coils as the motor's turning. Make sense? Lenz's law tells us that the current that is induced will oppose the change that created it. So basically, as a motor is turning, there's current that is induced in those armatures that will oppose the current that's creating the motor. And so the resistance goes up, is a way of looking at it. A turning armature in a motor has higher resistance than a stationary one. So when you have an electric motor that's rotating, there's more resistance and less current in the armature. If for some reason you jam that motor so that the armature stops rotating, the current goes, the resistance goes down, the current goes up, things get really hot, and your motor can burn out or blow up, okay? That's why it's really bad to have electricity running through a motor that's not being allowed to spin. Like in your blender. You turn your blender on, and if you jam something down in there and prevent it from spinning, it's going to get really hot and burn the thing out. We talk about burning motors out, okay? The idea, that whole concept is known as back EMF. So a rotating armature has a changing flux, and therefore it's inducing an EMF, okay? No, it's not. With cars, we're dealing. All right, so a rotating motor has more resistance than one that's not rotating. This is one of the reasons why your lights flicker when the motor cuts on your refrigerator, and why motors burn out when there's electricity running through them and they're not allowed to turn. They'll tend to cause them to get really, really hot. 10 minutes till bedtime. Okay, this is a transformer. This is a transformer, and this is one of the main reasons why we use alternating current. And it's a real simple device. So let's look at it for a second. It's basically two different circuits. You have what's called the primary circuit on the left, the secondary circuit on the right, or we call them primary coils and secondary coils. They are coils of wire, and then you have an iron core that connects these two different loops. So let's think about what happens for a second. If I send current into this primary coil, it will loop around, and what will it create? A magnetic field, just like a solenoid, okay? And in this case, use your third right-hand rule. You should be able to tell that this current going that direction is going to generate a magnetic field like so. Everybody with me? The iron core basically traps the magnetic field. The magnetic field stays in the iron core, so it will end up going around like this. All right? Now, just for fun, if this current was alternating current, what would that do to the magnetic field that it's creating? It will alternate the field, right? So then I have a secondary coil that has a magnetic field in it that's constantly changing. What happens when you have a constantly changing magnetic field in a coil of wires? You generate current, okay? So the alternating current in the primary coil will generate or induce current in the secondary coil. Now that seems really stupid because it's like, I had current in the first place. Why do I even want to create in the second place? What's the point? But the cool thing is, by changing the number of loops, I can change the voltage. Okay, if this secondary coil has more loops, I will end up with higher voltage. And here I will have lower voltage. So that's what transformers do, and they're really simple. Just because I have alternating current in the primary coil, I will generate alternating current in the second coil, and I can easily change the voltage by changing the loops in each coil. They're very efficient. You don't lose very much energy at all. They're very, very efficient. Okay. We had a great question. Direct current doesn't work in a transformer because with direct current, the magnetic field's never changing, and therefore you don't have a changing flux in the secondary coil, so you won't generate current in that second coil. All right? You may lower the voltage also. If you have more loops in the primary coil, you'll get a lower voltage in the secondary coil. So this is what transformers do. The reason we use a laminated core is because that reduces friction.
All CSAP partners, please bring your text before it.
All right, the CSAP announcement. Okay, so this is basically how transformers work. The laminated core helps reduce eddy currents in there, which makes them more efficient. They're really neat devices, and this is why we like alternating current, because now we have a way of bumping the voltage up or bumping it down very easily. Okay. So this is the essential model of our power grid. This is how we run our society, okay? We have these power plants way off in somewhere burning coal or natural gas or something to turn turbines to generate electricity. We want that to be at high voltage. So we create transformers that are called step-up transformers that bump the voltage up to super high voltages, 240,000 volts. I think even higher than that. I've heard 700,000 volts sometimes. Really huge high voltage. Big high voltage transmission lines take that electricity, take that power, transmit it across the countryside. When it gets close to town, you have what's called a substation, which has a bunch of transformers in it, which drops that voltage down. Things like in Godzilla, where the sparks fly and stuff, exactly. Then it's still pretty high voltage. We're talking about thousands of volts. And outside of your home, there's usually another transformer that drops it down to the 120 or 240 volts that we use. And here in Aspen, we don't see this very much because we've buried all our power lines. But if you ever go to a town that's a traditional American town with like power lines and running through the town or telephone lines, you'll see these transformers at the top of the pole. They look like that. You've probably seen one before. That's a transformer. It's taking high voltage, dropping it down to lower voltage before it gets into your house. And then again, like I said earlier, pretty much every electronic device that you plug in these days has a transformer in it to get the output voltage it needs for that particular device, which is usually less than 120 volts. The math with transformers is super easy. Super easy, okay? The voltage in the primary coil divided by the voltage in the secondary coil is equal to the number of loops in the primary coil divided by the number of loops in the secondary coil. Pure ratio. Pure ratio. Now, remember that power is equal to current times voltage, right? And a transformer can take low voltage and turn it into high voltage, but it's not doing anything to generate power. So in order to not violate the law of conservation of energy, if the voltage goes up, what must the current do? Must go down, and it does. And so that relationship looks like this. the current in the primary divided by the current in the secondary equals the number of coils in the secondary divided by the number of coils in the primary. So that one's flipped. Okay, more coils will give you less current, but more voltage. I do believe these equations are in your equation packet.